Hi, in this video we are going to look into the next chapter that is called process concepts. So boys and girls, this is the first chapter in process management. So as you know, we have seen so far introduction and backdrop, where what is operating system, functions and goals of operating system, and then we have seen services of operating system, types of operating system, and system calls. Now today we look into the first module, first chapter within the process management. Operating system is a constitution of collection of several modules, several subsystems, and the major subsystem is process management. So today we'll look into some of the foundations, some of the basics of process. What exactly is process? What exactly is program? And what is the relationship and difference between process and program? So this is my profile. And there is a disclaimer indicating that, again emphasizing that the whole content is from the operating system textbook by Galvin, Instructor Resources, that the slides are from this textbook as shared by the author. Okay. So therefore this is the name of the chapter, process concepts. So before I formally define what exactly is process, I would like to make a small discussion showing the relationship between program and process. So let's discuss this. Program versus process. Okay. So first point, I would like to make a mention that when I use the word program here in the context of operating system, whenever I use the word program, right? Essentially, I am referring to machine language program, low-level language program. I am not referring to high-level language program like C, C++ or Java or Python. So essentially, I am referring to a machine language that is .exe file, .exe program. So let me write. Program here refers to .exe, executable program. And as you know very well, executable program consists of two things. It consists of two things. One is instructions and the other is data. Instructions like, for example, load, store, and then read and write, or maybe in and out instructions you can say, or data transfer instructions, arithmetic instructions, logical instructions, and so on. And boys and girls, let me tell you that data is of two types as used in the program. One is called the static data. And this is my classification, my taxonomy. It's not exactly like what is the meaning of static in C, C++, essentially. So I mean static in the sense that the size of the data type is fixed and the allocation takes place before runtime. That is static. Dynamic means the allocation takes place during runtime. So this allocation takes place before runtime, and dynamic data in the sense that it is allocated during runtime and the size of the data is not fixed. It may be variable or it may even be fixed. Like for example, if you are familiar, the function like malloc or the operator like new in C++ essentially is the dynamic data. The memory which is allocated with malloc, the memory which is allocated with new operator is essentially the dynamic data. So that is about program. Then what is process? The formal definition of process, if you see, is program in execution. Program in execution. See, when you want to execute any program, you have to load that program. You have to load that program from disk to memory. So when that program comes from disk to memory, when the program gets loaded in memory, then that entity will become process. So program in execution state. Execution here, people often think that when it is running on CPU. No. Execution simply does not mean running on CPU. Execution means not only running on CPU, but also, for example, execution means when it is utilizing the resources of the system. This is the exact meaning of execution. Utilizing resources of the computer. Processor is only one resource, boys and girls. Processor is only one resource. So when it is running on CPU is in execution. When it is performing IO operation is in execution. When it is just present in memory waiting for the chance to run on CPU is in execution, because it is utilizing memory. When it is performing IO operation, it is in execution. So boys and girls, execution, don't think that simply means running on CPU. No. Execution primarily means utilizing the resources of the computer system. Okay. So a program in execution state is called process. So the entity when comes from disk to main memory gets stored in memory for the purpose of execution. It is called process. Process is active. Active means it is alive. It is utilizing the resources of the system. Whereas program is passive. These are the fundamental differences. Program is always on disk. Process most of the time is in memory. These are the essential differences between program and process. Okay. It is an active entity, alive entity. It is a schedulable unit which can get scheduled onto CPU. It is a dispatchable unit onto CPU. And one of the author, just to make an understanding, he said that process is like an animated spirit within the program. Boys and girls, you cannot see process running on CPU. Can you? No. Can you see the program on disk? You can see the program on disk. Program is like visible entity. Process is like an abstract entity. You cannot see process in memory. That's why we say process is like an animated spirit, alive, agile. Just like we believe there is a spirit inside the body. So process is like a spirit in the program. All right. Like for example, you take my case. I as a family member in my family. But when I come here to take the class, I am like a process. I am a professor, I am a teacher, I am a mentor. I am utilizing the resources of the system. Like camera is there, laptop is there, like smart board is there, pen is there, mic is there. These are the resources. While at home, I cannot use these resources. So I am passive at home, a simple family member along with my other members. Is it not? So there it is like program, here I am like process. So that's the difference and similarity between program and process. And I would like to make a mention that there is no existence of process without a program, obviously. There is no existence. There is no existence of process without program because process is instantiated from program, just like object and class. Process is created from a program. It is an instance of a program. That is another perception of process. So that I hope by means of these definitions you are able to have some clarity. So let's see the definitions. An operating system executes a variety of programs that run as process. A program in execution state, process execution must progress in sequential fashion because the instructions are executed sequentially, no parallel execution. The program code also called text section. We'll come to this text section. Current activity including program counter, that is called the environment of the process. I will talk about that shortly. What is stack section, data section, heap section? All these are the components of process which I will talk about shortly. Okay. So program is passive. This is a point I told. Program is passive, stored on disk in the form of executable file. Process is active entity. Program becomes process when an executable file is loaded in memory. So boys and girls, this is a very important point showing the relationship between program and process. I'm very sure after this discussion you should have extreme clarity so that you are not going to get confused between program and process. The execution of the program can start by textual commands or maybe GUI's mouse clicks. You click and then it starts execution. One program can be associated with several processes, very important point. Because it is an instance of a program, so from one program I can create multiple processes using mechanism like fork system call. If I use fork system call in my program, I can create multiple processes. Now coming to the process structure, I would like to spend some time on this. I would say, what is the abstract view of process? Abstract view of process. How does process look like in memory? Important discussion from interviews perspective. How do process look like from memory? Please observe this. Just now we made a mention that process is created from a program, and once again I reiterate, program consists of two things: instructions and data. Okay. So the organization of these instructions and data units along with other components in memory and shown in the form of a block diagram is what is termed as process structure in memory. Process structure is what is termed as process structure. How do process look like in memory? Somebody may ask you, you cannot see process in memory. Yes, you cannot see. But can we imagine the process structure? Haan sir, we can imagine. So how do process look like in memory? Tomorrow in the interview, the interviewer may ask you, show on the piece of paper, what are the important components of process, or he may ask, what is the block diagram of process in memory? How do process look like in memory? Is the point. So the first thing is, as you see here, it will contain what is called the text section, the first component. Text. This is also called code section. This text or code section of the process structure in memory invariably contain nothing but all the instructions. All the instructions of the program are taken and accommodated here, text and code section. And then I have the global data section. It's called data. Or maybe I will write with the white color. It's called the data. So this data again is of two types. Two types, as we shall see at later point of time also. One is called initialized data and the other is uninitialized data, global data. So essentially this is global variable. The global variable that you use in C, C++, they are put here in this section, global data. And after that we have the heap section, as I said, dynamic data, right? So that is basically heap section. This is the heap. Because this can grow and shrink, this is dynamic, so therefore I put an arrow to indicate that it can grow and shrink. So what will this heap contain? Heap basically is that portion of the process structure in memory where we allocate memory, where we allocate space using DMA, dynamic memory allocation, using functions like malloc and new. That is heap. Last part of the process structure is stack. We say runtime stack is user stack. Apart from kernel stack, I will have user stack. Every process will have user stack. This can grow and shrink. What does this stack contain? This stack contains, very important point, activation records of function calls. As you studied in programming, whenever we make a function call, right, we have to push an activation record onto the stack containing local variables, formal parameters and other important fields, return address, activation records. So for each function call, I will have an activation record pushed onto the stack. If you remember recursion is impossible without stack. So the purpose of stack is to store the recursive calls, activation records of the recursive stack. So boys and girls, this is what is termed as the process structure in memory. This is how the process look like in memory. So boys and girls, if you remember that process is an abstract, it's like abstract data type, ADT. Being an abstract data type, it will have definition, it will have representation. This is the representation or process structure in memory. So you can call this as process structure in memory. This is how the process look like in memory. Fine. Then we have next process operations. Every operating system will provide mechanism for performing various operations on process, like what? Process creation, process deletion, scheduling the process, synchronizing the process, dealing with deadlock management, dealing with synchronization. All these are operations which are performed on behalf of user by the operating system on process. So process, being an abstract data type, support operations. And lastly, process is associated with attributes, properties, characteristics. As a real life entity, process is associated with a well-defined list of attributes. What are the attributes? Like for example, I as an entity in this universe, in this world, is associated with attributes. What are my attributes? My attributes are my name. If I am having an ID, in my organization I have an ID, employee ID, employee ID. Then my age, my weight, my color, my height, my address where I stay, my designation. Is it not? All these are attributes. So boys and girls, like that, process as an entity within operating system is associated with several attributes. We have identification related attributes. For the purpose of identification, every process is associated with the process ID. And the parent from where it is created, parent process ID. If the process belongs to a group, group ID. Program counter, general purpose registers, priority, state of the process, these are the attributes related to identification. And then CPU related attributes, state of process, program counter, general purpose registers, priority of the process, okay. Then memory related attributes, size of process measured in bytes. Memory limits where the process is stored, like depending on memory management, if I use paging, page table address, page table base register, PTBR. If the process is using some files, file IDs, file descriptors, the list of files in use by the process, list of devices which are in use by the process, other accounting information. So all these attributes are there associated with process, and these attributes of the process are kept in a table, a data structure which is called PCB, process control block or process descriptor. Shortly I will display that. So boys and girls, summarizingly I am saying that process as an ADT is associated with its definition, with its representation or structure, operations and list of attributes. So now if you go back to the slide where I have explained this point, you can see current activity, which instruction, or before that the program code also called text section I have demonstrated. Current activity is included by program counter and other process registers. Stack containing temporary data, function parameters, return address, local variables. Data section containing global variables. Heap containing memory dynamically allocated during runtime. These are the important components of process in memory. A very important point. This is a useful interview tip. Useful interview tip. So that is a process structure. You can even see this diagram from Galvin textbook. Text is here, data, global data, initialized and uninitialized, heap section and stack section, and that is growing in this direction. Addresses are going in this direction. Boys and girls, this is a memory layout of C program showing the correspondences in process structure. These are programs in high level mode and its equivalent data structures which are mapped into the process structure. You can check here. These are anyway header files. We don't have to bother about this. This is global variable. So look at this. This is uninitialized global X. So it is going into uninitialized data, and this is going into initialized data. This is the data part of the process. The instructions will come into text part. And now the argc argv, as you might have studied in programming, these are called command line arguments. Command line arguments are stored over and above the stack in argc, argv. And then I have local variables. Look at this. Values and I, local variables. Where will they get stored? In the stack activation record. So it gets stored in stack. So suppose this dynamic memory allocation malloc, look at this malloc. So whatever memory is allocated, that will be allocated from heap portion. A very good correspondence. And suppose, for example, if you have instructions associated with this code, these instructions will be stored in text, not indicated, but I am telling you. That will get stored in the text part. So the boys and girls, this is a very good example to show the correspondence between the program elements and the process structure elements or process structure in main memory. So that's what we said, memory layout of a C program with regard to process. So I said basically up to this particular point, I would say you should have extreme clarity. What is a program? What are the constitutions of program? What is a process? Difference and relationship between program and process. What are the elements of process? All these basically are important. Okay. So just now I said every process will be associated with a list of attributes called process attributes, which are stored in a table called process control block. After this, I will show you that process control block structure. Okay. One of the important attribute of process is called process state. During its lifetime, the process goes from one state to another state. During its lifetime, the process goes from one state to another state. So here we are going to learn what are the different states in which the process can be in during its lifetime. So boys and girls, it's a very famous diagram which I am going to present now. But before that, let us understand what are the different states the process can go during its lifetime. The various states are as follows. The very first state is called new. What happens in new state? The process is in the process of getting created. We are allocating the resources which are necessary to create the process. It is in the transition to go from from hard disk to memory. That state is called new. And once the process has been created, it becomes what is called ready. It changes its state to ready. Ready means what? It is ready to run on CPU. Ready to execute instructions on CPU. So the process is waiting to be assigned to a processor, ready. And in a typical multi-programmed operating system environment, I can have many ready processes. I can have multiple ready processes, multi-programming. Whenever the process gets scheduled onto CPU, the state changes to running. So running means instructions are being executed on CPU. And whenever it is running and need to go for IO operation or it execute any system call, the state of the process changes to waiting. So waiting is also called block. The process is waiting for some event to occur. That event could be like, for example, input output, or it could be execution of any system call, or it can be waiting for some interrupt also. Anything, event. These are events. And finally, when the process completes its execution, it changes state to terminated. The process has finished the execution, so all resource deallocation takes place. Whatever resources the process was given, that deallocation happens. So new state resource allocation, terminate state resource deallocation. So in between new and terminate, I have ready, running and block. So these are called the famous 5 states of the process, and the transition that the process can make during its lifetime is shown by means of this diagram, which is generally termed as process state transition diagram. Process state transition diagram. So let me bring it here. Okay, process state transition diagram. That means showing what are the transitions that the process can make during its lifetime as it goes along from one state to another state. So it's a very clear diagram. The very first state here is new, where the process is getting created, resources are getting allocated. So once it is admitted into memory, it becomes ready. I can have multiple ready to run processes. Whenever CPU is idle, we select one of the process, that is called CPU scheduling. We select one of the ready process and then it get dispatched onto CPU, where the process start running. Now when it is running, several events can happen. Basically it get completed, so therefore it go to terminate state. Our running process may go for some IO operation or event, so it leave the CPU and come to waiting state, also called block state. Okay, so this going from ready to running is called scheduler dispatch. And when the process complete the IO operation, when it complete the IO operation, IO or event completion, the process become ready to run. It cannot come back to running state because somebody else might have taken the charge, so therefore it has to go to ready state. Okay, our process running may get interrupt and then timer interrupt, times out like round robin, it will come to ready state. So boys and girls, this process state transition diagram is a clear illustration of a preemptive based multi-programmed operating system. So it is a clear illustration of preemptive based multi-programmed OS. Sir, how do you say it is preemptive? It is preemptive because of the presence of the transition from running to ready. For this transition, we are saying it is preemptive. Because this is forceful deallocation. These are natural deallocation. Completion and IO is natural, non-preemptive, but this is preemptive. So boys and girls, if I remove this transition from running to ready, then it becomes non-preemptive multi-programmed OS. So this is a simple process state transition diagram of a multi-programmed operating system with preemptive in nature. And if I remove the ready state, then it becomes uni-programmed OS, because in uni-programmed operating system, I can have only one process present in memory. The presence of ready state indicate that this is a multi-programmed operating system environment. As long as a process is in ready state, running state, waiting state, it is in main memory. It is in main memory. Sometimes it happens that I need to suspend the process, swap out, roll out the process from memory to disk. So that we are not indicating here, and after some time I will talk about it. For better performance, improved performance, I have to suspend the process. Performance of the system may be degrading, declining. So the only option left over to operating system is to suspend some of the partially completed processes from memory onto disk. That is called process suspension. So I may suspend from running state, ready state and waiting state, but the most prominent state for suspension, desirable state for suspension is ready state. When it gets suspended, it will go to disk and again later come back. We'll talk about it after some time. So boys and girls, this is what I was talking about, the concept of process control block, also called task control block. Look at that, process control block or task control block, because in operating systems like Windows, instead of using the word process, they use the word task. So boys and girls, task, process, application, all these are same. All these are same. So like I have process state, running, waiting, etc. Program counter, CPU register, CPU scheduling information, memory management information, accounting information, input output status information. All these are attributes of process which are stored in a process control block, in a data structure. This is one of the important data structure of the process. So each process during its lifetime is associated with PCB. And in my interpretation, I used to say PCB is like a ID card of the process, or like in the context of our Indian environment, subcontinent, you can call it like Aadhaar card. It is like Aadhaar card. Aadhaar card gives complete picture of the entity of the person. PCB gives the complete information about the process, where it is, what instruction it is executing, right? And what is its state in memory, how many bytes it has used, what are the resources it has used. Everything about the process can be found from PCB. So this is PCB, boys and girls. PCB, process control block, also called process descriptor. And I would like to also tell you, I would also like to tell you that the whole information kept in PCB, the volume of information kept in PCB is called process context. Process context. Content of PCB is known as process context. The volume of information kept in PCB is called process context. And sometimes even process context is called process environment. Process environment. Remember this term. And it is only from this term, process context, that we have a term in scheduling called context switching. If you have followed, if you have heard that context switching, the word context is nothing but the content of PCB. Chalo, next. So these are just a representation of the C programming structure, task structure in Windows, like for example, showing how the process attributes are kept in PCB. Like I have PID, state, time slice, parent process ID, children process ID, and then list of files, and then the address space of the process, process identifier, state of the process, all that is stored. It is like a linked list. These PCB are one process, another process, like that. It is in the case of Linux. Okay. And I will talk about this scheduling shortly. Here or before this, I would like to tell a topic, scheduling queues. Scheduling queues. So let me write it again. Okay. So scheduling queues. Please remember, boys and girls, every multi-programmed, very important topic, every multi-programmed operating system maintains a list of queues. The queue data structure which you studied in data structures, list of queues, scheduling queue, known as scheduling queues. There are two types of queues used by operating system. Let me tell you, there are two types of queues. Every multi-programmed operating system supports two types of queues. One is called in-memory queue, the queues in memory, and the other is called on disk. On disk. And boys and girls, let me also emphasize that in memory there are two queues, and on disk there are two queues. What are in-memory queues? One is very important predominant queue, and that is called ready queue, and the other is called block queue. Conceptually, you represent a ready queue like a rectangle here in the form of a block diagram, and a block queue is also represented like that. So this is the ready queue pointer. Actually, what is this? This is nothing but a list, linked list of what? Of PCBs, process control blocks, of those processes that are ready to run. I may have PCB of one process, another process, another process, another process. And block queue, like for example, process may go for IO operations. So for every device, input output device, I may have a queue known as device queue. This is device Q1, I may have like that device Q2, and this also contains PCBs of the processes. So ready queue is a representative of ready state, and block queue is a representative of block state. Then what are the queues on disk? As I described just now, basically on disk, the one important queue is suspend queue. Just now I made a mention that sometimes the processes have to get suspended. I will push out, swap out from disk, from main memory to disk. So I should have some area on disk where I am going to store the process. So that area demarcated for storing the suspended processes is termed as suspend queue. And in some operating system, not all, we may also have a type of queue which is called job queue. which is called job queue and sometime also called input queue. What does this queue contain? In case if I cannot load all the programs into memory, then ready to be loaded programs are kept here. Programs to be loaded in memory. To be loaded in memory. Suppose if I can load all of them without any queue, then there is no need of this job queue or input queue. In some operating systems I may require. So showing these queues in the form of block diagram, you can check here. See this. The first one is ready queue. It has a header and tail pointer, head pointer and tail pointer. So what does ready queue contain? Ready queue is nothing but a linked list of PCBs, process control blocks of those processes which are ready to run. This PCB of some process 7, PCB of some process 2, and these are end tail pointer. Why we are having tail pointer? So that we can add new PCBs at the end. Like that is the waiting queue or block queue. Per device I can have its own queue. So this is a device queue containing PCBs of the processes that are blocked for performing IO operation from this device. Finally, this is what is called queuing diagram. This is called queuing diagram. Okay. This is called queuing diagram. This is queuing diagram. It shows all the queues. Like here I may have input queue. From input queue, new processes get injected into ready queue. May get injected into ready queue here. And whenever CPU is idle, one of the processes is taken and scheduled onto CPU. And when it completes, it will leave the system. Suppose if it need to go for IO operation, right, input output request, it will be added into IO queue. And whenever the IO operation is over, it will come back to ready queue. So new, ready, running, terminate, and this block. And suppose if timer goes off, running process times out, it will directly come to ready queue without any blocking, come to ready queue. If it creates child process, child termination, waiting queue, child process terminate, then the parent process will come back to ready queue. And I'm waiting for some interrupt to happen, for event to happen, I'm interrupt wait queue. Then whenever interrupt occurs, the process will come back to ready queue. So boys and girls, this is a very clear diagram. It is called queuing diagram, state queuing diagram. It shows the state, new, ready, running, terminate, block, right? So queuing diagram. So this is called process scheduling basically. The word scheduling implies, making a selection. The word selection, scheduling implies making a decision, making a selection. Like I have to select, so for that there will be an operating system component, we'll talk about that later. So whenever CPU become idle, I have to schedule one process onto CPU. Whenever there may be many IO requests pending, whenever IO request is completed, I have to schedule one process IO request to get completed onto the device. So all that is called scheduling. And context, which I will talk about shortly. I'll come to this later. This is a diagram showing the process creation. I think I will discuss this shortly. But before that, I would like to make a discussion on this, a simple topic where I say, let me see, schedulers and dispatcher. Schedulers and dispatcher. They are important topic again. Every multi-programmed operating system implements 3 schedulers. Just now I said scheduling implies making a decision. So the components which are supposed to make decisions are called schedulers. The operating system modules, programs which are meant for making decisions are called schedulers. So in the realistic multi-programmed operating system, we have 3 types of schedulers or 3 schedulers. One is called long-term scheduler. We write in short generally LTS. Second is called short-term scheduler. and this is written in short, let us say it's TS. And the third is called medium term scheduler, MTS. What is the job of short term scheduler? So first I will start with short term scheduler. Short term scheduler is responsible for making a decision which ready process should run next. So essentially I would say short term scheduler operates on ready queue. It operates here. Who should run next onto CPU? So it is supposed to work on ready queue, deciding which ready process should run next onto CPU. So invariably I am compelled to write here saying that short term scheduler sometimes is also called CPU scheduler. We have a next chapter on CPU scheduling. So the short term scheduler is nothing but the module which is responsible for deciding who should run next onto CPU. That is CPU scheduling. That is CPU scheduling. Which ready process should run next? So I have different criteria implementing different scheduling techniques. So short term scheduler. Like that, if I have a job queue, boys and girls, if I have job queue, multiple programs are stored on job queue. So who should get loaded into main memory? That is decided by long term scheduler. So I would say here, long term scheduler operates on job queue, whereas short term scheduler operates on ready queue. Ready queue. I've already told about this. And finally, sometimes I need to suspend the process. So suppose if I am suspending the process, it will go to a suspend queue, SQ, suspend queue. Again, I will bring the process back into main memory. So for that, who should be suspended, who should be resumed? That is decided by medium term scheduler. So basically, medium term scheduler operates on suspend queue. So the concept of suspension and resumption, the concept of suspension and resumption is done by medium term scheduler. Medium term scheduler. So these are the three important schedulers that are present in multi-programmed operating system environment. Then we have a last module which is called dispatcher. So let us talk about dispatcher. What is the role of dispatcher? So here we will see. Dispatcher. What does dispatcher do? Dispatcher is that module of operating system which is responsible for carrying out an activity called context switching. Context switching. Okay. What is context switching? What is context switching? Context switching is an activity of saving and loading the PCBs of processes on to or from CPU. Loading and saving the PCBs. To understand this ideology, so therefore context switching is an activity carried out during a process switch. So imagine, for example, this is ready queue, and say for example this is a CPU, and also we imagine, for instance, this is some device queue. So understand this scenario to really follow what is context switching. This is ready queue, this CPU, and this is some device queue. And you can imagine, for example, there is some IO device here. This is some IO device, IOD. So let's imagine that I have some processes here, PA, PB, PC, which are ready to run. And on CPU, let's imagine PR is running. After some time, if PR needs to go for IO operation, then I have to basically save the PCB of this process here into device queue, save. So who is going to do that? That is done by this module called dispatcher. So PR leave the CPU, right, and get its context saved into sys. Already some processes may be there here, PI, PJ, PK. So PR get added. Now CPU become idle. Short-term scheduler decide who should run next. Suppose I decide PB should run next. So from this linked list I have to delete the PCB here and load it here. This is called loading the PCB. Loading the PCB and saving the PCB. This activity of load and saving the PCBs is carried out by this module called dispatcher, and the time needed to carry out this load and save operation is called context switch time. Context switch time. Sometime context switch time is also known as Context switching time is also known as dispatch latency. Dispatch latency. Latency means delay. Delay in loading and saving. Naturally, if the size of PCB is more, I need more dispatch time, I need more context switching time. So context switching time invariably depends on the size of PCB. So, and moreover, context switching time, when context switching takes place, the processor cannot do useful work. So therefore, we say context switch time is an overhead. We would like to minimize the context switch overhead. It's an overhead for efficiency or the throughput of the system. More the context switch time, more the overhead, and less efficiency or less throughput. So the same thing is shown over here. Context switch occurs when the CPU switches from one process to another. So here process P0 is executing, it generates an interrupt. I am saving the state of PCB 0, of process 0. Then till this time process P1 is idle till this time. I am reloading the PCB of state PCB1. Now PCB1 get activated on CPU. So process P1 start executing. An interrupt or system call. So this get saved. I mean we are saving the PCB of P1. Again this fellow is idle. And at this particular, during this time from here to here, process P0 is idle because it was waiting for its IO. And then whenever IO or system call is over of P0, it start reload the state of PCB0 and execute. So that's how I'm switching from one process to another process, and these are the sequence of events demonstrating that. So now read some comment. When CPU switches to another process, the system must save the state of the old process and load the saved state for the new process via a context switch. So this is the main definition of context switching. A very important term as far as interview is concerned. Context of a process, I told this point, boys and girls. Context of the process is represented in the PCB. Context switch time is overhead. The system does no useful work while switching. The more complex the operating system and the PCB, the longer the context switch. Time dependent on hardware its support, the context switching time. Some hardware provides multiple sets of registers per CPU. So multiple context loaded at once. So it is purely a hardware activity, right? It is purely dependent on the hardware. Then as a case study here, I'm going to show you the system called fork, which we discussed last time. So different system calls like fork to create a process, and then exec to execute a process in the child address space. How we can do that? Let's understand by means of this diagram. So address space means the area in memory where the process is loaded. Child process get duplicated from parent. Child has a program loaded into it. And this is an example taken from Unix, and realistically you can also execute on Unix or Linux machines. Fork system call will be used to create a new process, and exec system call will be used after a fork to replace the process memory space with a new program. Some program I will show you. Parent will wait until the child terminate. So the cycle, the sequence diagram that we are going to implement by means of a C program using this system calls is something like this. So first I am going to fork, that is going to create a child process. Parent PID greater than 0 means this parent. So parent is waiting till the child terminate. What will the child do? Yeah, I mean in the earlier session I told if the return value is 0, then that is a child process. The child process will execute the code of some program and exit. So how this functionality can be implemented, you can see. And these are a tree of processes in memory. Generally the processes get created from other processes like this in the form of a tree structure. That program which I was talking about, I would like you to have a close look at this, and it is highly desirable, boys and girls, that you try to implement this program to get a feeling of system calls. Okay, everyone, those of you who are watching this video, my advice would be to basically execute this program realistically on a Unix or Linux machine, or even with C online compiler you can do that. So execute and see get the feeling of system calls. So just for a minute, pause the video and then you try to read the code and make an understanding what is happening. Okay, that sequence diagram which I explained is being implemented by means of this program. Just glance through the code for a while. So see here, these are the header files first. sys.types.h, studio.h, stdio.h, unistd.h for system calls, type declarations. So PID, Fork a child, this is a fork, this is a system call, first system call used here, let me underline it. If PID less than 0, fork failed, terminate. Otherwise, if PID is 0, this is a child. Child is executing a system call by name exec, and within that we are executing a program by name ls. In Unix and Linux, ls is basically, this is not 1s, this is ls please. This is ls. ls is program, ls in Unix basically list the files in current directory. List the files in the current directory. So name of the program, this is the path /bin/ls, name of the program, and we are not supplying any arguments. So therefore null. That's the syntax of exec. So first system call is fork, second system call is exec. Now else means PID is not 0. PID is not 0 means PID is greater than 0. So therefore that's a parent process. So parent will have to wait for the child to complete, and for that I am using another system call by name wait. So in child process, when I say wait on null, I am waiting for the child which got created earlier to terminate. So boys and girls, this is a simple program illustrating the three system calls fork, exec and wait. So after that I'm saying that child completed. So my advice would be to write this program if you have a Unix machine, Linux machine, or if you don't have Unix and Linux, simply open any browser and then you say C online compiler, you will get the interface, type this program and check the results. That will be a good idea to basically get a flavor or idea of system call execution. Okay, so same thing, explanation is here. Process execute last statement and then ask the operating system to delete it using exit system call. So exit system call return the status from the child to parent via wait. Process resources are deallocated by operating system. These are the sequence of event that happens during process termination. Okay, during process termination. And there is something called cascading termination that implies all the children, grandchildren and all are terminated. Some operating system follow. These are only design issues. Design issues. Okay, termination basically done by the operating system. And in multi-process architecture like in Chrome browser, each of the applications that you launch correspond to one process. These are all different processes. That is what I am trying to say. Boys and girls, please observe. Each tab that you open in Chrome browser, for example, represents a process, separate process. So main Chrome browser is one process, and from there you are creating several processes as child processes. So many web browsers run as a single process. If one website causes trouble, the entire browser can hang or crash. These are the options. Google Chrome browser is multi-process with three different types of processes like browser itself, renderer processes, and then sandbox. These are the things which can run. So that is the meaning of this. So boys and girls, this is what I have in this chapter, process concepts, where we have seen, if you have any queries, you can basically direct the queries to me through Telegram channel. This is the QR code of my Telegram channel, and that is the QR code of the Geeks for Geeks site website. And here even my official email ID is there. So for any queries, any doubts, any clarifications, you can shoot your email or you can get it touch with me through Telegram channel. Okay, my Telegram channel ID. So in this chapter we have seen what is program, what is process. Difference and similarity between program and process. Process as an entity is associated with, treated like abstract data type. And being an abstract data type, it has a structure in memory that is called process structure, process layout in memory. What are the important components of process we have seen in memory? That is nothing but code section, or also called text section, and then data section, heap section, stack section. And the correlation of program elements to this process structure I have shown. Then we have seen process operations. What are the operations that can be carried out on process? Then we have seen what are process attributes. Categories of attributes, identification, CPU related, memory related, device related, file related. And then we talked about the concept of PCB. All the attributes we said are associated, are kept in PCB. And one of the important attribute is called state, process state. During its lifetime, we said process can go from one state to another state. So we have seen what are the different states: new, ready, running, block, terminate, and how the process can go from one state to another state. We have seen that by means of process state transition diagram, preemptive and non-preemptive both. Then we talked about the scheduling queues. ready queue, block queue, device queue, and suspend queue, 2 in-memory queues, 2 on-disk queues. Ready queue is a representative of ready state that contain linked list of PCBs of those processes that are ready to run. Similarly, for every device, input-output device, the operating system would maintain a separate device queue containing PCBs of those processes that need to get themselves serviced from that device queue. Like that, I can have any block event corresponding queue. When process gets suspended, swapped out, rolled out from memory onto disk, it will be kept onto disk, suspend queue. And then we talked about the concept of dispatcher doing an activity called context switching. Very important. It's an overhead activity. And then finally, as a case study, how using fork mechanism, we can fork exact demonstration of various system calls to create process and execute some program in process. So boys and girls, this was the discussion as a foundation for other topics of process management, other chapters of process management, namely called process concepts. So in the next videos, we'll start the discussion with one of the most important topic in process management, and that is called CPU scheduling. Till then, take care. Thank you and goodbye.